I'm really thrilled to welcome Eugenia Cheng to talk to us about her book. Thank you, Eugenia.
Thank you very much. Well, first of all, I'd like to thank Gershom and the other organizers for inviting me here. Thanks for coming. This is the widest room I've ever spoken in. So I'm going to have to do a kind of tennis match type thing. This is going to be a meta talk, because I'm talking about how to bake pie. The organizers asked me to talk about my experience of bringing abstract concepts to a wider audience, which is something that people have often told me is not possible. And there are, unfortunately, many category theorists who say, well, there's no point trying to explain this to other people because it's too difficult, or because the void is too wide and we will never bridge that gap. And, of course, when anyone tells me something is too difficult, I immediately go, well, I better try and do it then. And so this is what I've done. And so I wrote this book to bring the ideas of abstract mathematics to everybody. And that's what I'd like to talk about today. And it's something that I have done, as Gershom said, for many, many years, just a couple of years. But for some years, I have been really involved with explaining abstract mathematics to people who thought they weren't going to understand it. Because, of course, the people who already understand it, I mean, that's fine, they already understand it. But even with this book, my publishers kept saying to me, well, who's your target audience? You have to pick one target audience. And I was going, I don't want one target audience. I want my audience to be everybody. I think that this, and it has turned out to be true, this has been read and appreciated by everybody from the youngest people I've met so far have been some 7-year-old children. They're the youngest so far who've read and got really excited about it. And then there are high schoolers who already are excited about math and often science or coding, and who want to find out more about it that's not just the greatest unsolved problems or something, but how to think about it. Then there are also undergraduates who are interested in going into research. There are grad students in category theory who want to do category theory but can't quite get their way in, because there are, of course, the extremely dry textbooks, and there are these strange YouTube videos by somebody or other. But then there's also adults who kind of fell off the math thing, who start slightly regretting that they fell off it. And 10 years ago, when I told people I was a mathematician, they would, non-mathematician types, they would mostly go, oh, I could never do math. But nowadays, people are much more likely to go, oh, I wish that I understood that more. And they're starting to regret a little bit that they don't. But then there are parents whose children, there are quite a few parents I meet whose children are more into math than they are, and they're worried that they don't know how to help their children or how to talk to their children about it. So they're reading it. And then there's the odd, very specific group of audience, which is the families of category theorists who want to finally have some clue about what their family's been doing all this time. And sometimes the response I get is, well, I understood all this, but it's not really math, is it? And I like to think that's because they think of math as things that are dull and unintelligible. So if something is fun and intelligible, they immediately assume it can't possibly be math. And in fact, it is math. And that some of the things that are, of course, the book isn't very technical, because if it were very technical, then, yeah, that would go over people's heads. You can't write one book and get them to understand graduate level category theory. But my aim is always to convey what the ideas behind it are. And that's often what isn't there in any of the other things. And that's what I always try to do in the Catsters videos as well, to just give a way in. Because if someone is motivated, once they've got their way in, then there's plenty of stuff they can read. But not knowing what the idea is behind it makes technicality very difficult to grasp. Because if you don't know why it's there, then you have no way of getting started. And so this is how I talk about abstract mathematics, showing some ideas behind it, using concepts that everybody can grasp, despite the fact that usually, we'll see, we're going to get to things that you don't usually see until you're really actually doing graduate level category theory. And so the things that I talk about to get people into it are Bach, juggling, hair, factors of 30, cake, custard, and in fact, the English title of the book is Cake, Custard, and Category Theory, but it was decided that Americans don't know what custard is enough. Or if they do, they think of it as some kind of extremely specialist, very, very kind of fancy food, which wasn't the idea at all. Custard in England is nursery comfort food, and so the title had to be changed. But now, since the American stuff is kind of things like The Late Show is worldwide, and so the English publishers have decided to actually switch to the American title because the American title has kind of taken over the global publicity. So first of all, the first problem is persuading people that math isn't just numbers and equations. And this is something that everyone kind of gets into most people get it into their heads when they're in elementary school. And for some reason that I still don't understand, I always knew it wasn't that. And that numbers and equations are a bit boring. And that math is something that's much broader reaching and much more illuminating than just numbers and equations. So math, I think, is the study of how things work. But not just any old things, it's the study of how logical things work. But it's not just any old study of how logical things work, it's the logical study of how logical things work. And the trouble with that is that nothing is logical. I'm not logical, you're not logical. I mean, I don't know what you think, but I'm pretty sure my computer's not logical. At least it doesn't feel that way to me. And so nothing actually works logically. So the first problem you get into is that in order to study anything logically, you have to move away from the world of actual things. And you have to forget or ignore all the annoying details that make things not work logically and move into the world of ideas. And that's the process of abstraction, which takes you from the world of real actual things to the world of ideas. And that's immediately a place where people get scared because they're used to real actual things. And the world of ideas, it sort of floats around nebulously somewhere. And what I try to persuade people is that yeah, there are pluses and minuses. The world of actual things is the world that we live in, but the world of ideas is the place where everything works properly. That's why I like math. And if you can persuade people of that, then that's a start, I think, to persuading them that abstraction has a point. And in fact, aside, I'm teaching a course called The Elegance of Abstraction at the School of the Art Institute of Chicago. So that's where I'm based now, where I'm teaching, and it's all art students. And they're all taking this math class, which is basically category theory. But I bill it as this is a way of thinking about things abstractly. And they're art students. They love thinking about things abstractly. It's all they do in art. So if there were a piano in here, which I don't think there is, I would now play you this piece of Bach. But it's the second book, from the second book of Preludes and Fugues. Of course, one could give a whole talk about Bach and math, and that's a separate talk. But this is the G minor prelude from the second book of Preludes and Fugues. And the first time I studied this piece, I'm a pianist as well, I got really confused by it because I couldn't follow the lines of music. And I don't know if you know about Bach, but it's actually someone was busking Bach on the subway platform where I got on the subway just now. She was busking cello suites on a viola. It was great. It's great because, another side, in Chicago, it's really, really stringent. They're very anti-busking, and so there are only 2 platforms where you're allowed to busk if you're actually going to get a permit. Anyway, so I liked that, and I love Bach, and this piece is written, as many Bach pieces are, polyphonically, so there are separate lines of music that run around each other, and each individual one is its own line of music. And I got confused by this because I felt like I couldn't follow the lines of music around. And so I thought, oh, I'll perform some abstraction on it. So I drew a diagram of the lines of music and how they interact with each other. And this is a very, very, very abstract version of the piece because I've forgotten almost every detail. So I say to people, abstraction's really fun because you get to forget details. I love forgetting details. My mother thinks it's because I'm lazy, which I am. And I always say to my students, being a good mathematician is all about being lazy. You have to not want to do the complicated calculations. And so you have to want to find some theory that will do the calculations for you, because then you can just do the theory, which is more fun than doing the calculations. So my students who aren't lazy enough, it's terrible. They'll sit and do pages and pages of really disgusting calculations, and I go, how can you have wanted to do that? Anyway. So this is my diagram of that piece of Bach. And then once I drew this diagram, I understood why I didn't understand, which is always a start. I understood why I didn't understand the piece of music, because the lines of the music cross over each other and then they don't come back again. And that's why I got confused. So if you tried to get 4 people to sing this in soprano, alto, tenor, bass, the soprano, who's the black line starting at the top, would have to end up as the tenor. And the bass, who's the red one at the bottom, would have to end up as the alto, and most people can't do that. I know one person who can sing soprano, alto, tenor, and bass, but that's only one, and he can't do it all at once. So this is my first illustration of how abstraction can help you. So it doesn't mean that in order to listen to the piece of music, you have to know that that's going on. And when you do listen to the piece of music, you probably can't actually tell it's going on. But it helps me performing it to know it's going on because it gives me clarity about the internal structure of it. And the structure here has come entirely from the relationships between the different parts. Not between what they're actually doing, but between from the relationships between them. And of course, this is a key starting point for category theory, where we study everything by the relationships between each other rather than from their intrinsic properties by themselves. And it's true about all sorts of structure inside things. So unfortunately, we go around telling people that they should study math because it's really useful. And then they grow up and they discover they don't use any math in their daily lives, so they realize we were all lying. And then they don't listen to anything we say ever again. So that's bad. And what I want to say is that it's not that you should expect to need to solve a quadratic equation in your daily life. It's that this stuff is going on everywhere, and that if you understand the logical structures inside things, then it helps you understand everything that's going on, even if it's not actually an equation that you needed to solve somewhere. And it's just like, I like to say, that I don't know where the structure is in this building. I don't know which walls are structural and which ones are not. But it's a good thing that somebody does. It just doesn't have to be me. And so in this piece of Bach, you can still appreciate it. And I like to say this is true of math as well, although we haven't previously done this very well, that it's possible to appreciate math kind of as an observer, even if you can't do it. And so my aim isn't to get everybody to become a researcher in category theory, although that'd be nice too. But I don't think that's a realistic aim. But I think it's possible to get everyone to experience some appreciation of it, just like you can listen to music even if you can't make music. And you can eat food, thank goodness, even if you don't know how to make it. And if you're like me, if you eat a really great food, then you kind of want to know how it was made. And it's exciting to discover how it was made, whether or not you're actually going to go and make it yourself. So if you're me, you're likely to go and try and make it yourself, and you might fail, but it's still fun. So that was the Bach braid, and of course braids are something that mathematicians do study, and I started studying those in my PhD, and I drew that braid about not that long before I started my PhD, a little bit before. But this is related to juggling. Now, can someone in the room juggle? Do you want to do a juggling demonstration? How about we get some fruit? Is there some fruit? No, there's no. Is there anything to juggle with?
Yeah, we'll juggle the melon slices, but that we're getting He's got fruit. How much fruit do you want?
3?
Okay.
Do you mind if we juggle with them? Of course, Gersham's going to be brilliant at it, so nothing will fall on the floor.
Are you sure there's no other jugglers in the room?
See, I tried to learn how to juggle just for the purposes of doing math demonstrations, but I'm really terrible at throwing, and I'm really terrible at catching as well. So it was kind of a doomed exercise.
This was not planned.
Yeah, I forgot to warn you about this. Oh. Keep going. Okay, now can you walk across the room while doing it? Very good. Woo! Keep going. So if I drew a picture, or if we had a long exposure camera of him juggling across the room, this is the braid it would make. So you have to imagine that the clementines or satsumas or something are 3 colors, and as you throw one of them across from your right hand to your left hand, you walk this way, and then you throw the other one across to thank you. Woo! And then you throw the other one across, and one of them's definitely going across the other one, and so that they get looped up like that. And this is, I forgot that I was supposed to do my hair like this, but if you braid your hair, then that's exactly the same thing. So you bring one across, the right hand one across, and then the other, I did the left, the right hand, and then the left hand one across, and then the right hand one across, and then the left hand one across, and so on. And if you do it while walking, then you get a 4-dimensional braided surface. So that is the same braid that you get from juggling. And the thing, mathematicians study these, and you study things like how looped up are they? Could you pull this apart just by moving some of the strands around? And the answer, as we all know about braided hair, is that you only need one hairband. I've got 0 hairbands. But if you only need one hairband to hold that in place. So, of course, one day, inevitably, I thought, oh, I'll try doing the Bach braid in my hair. And that doesn't work at all. Because you need to hold it. You need so many bands to hold it down that it becomes completely futile.
That's called a saraband.
But mathematically, it's to do with the fact that in mathematics, we say then that if we held these points down at the top and these points down at the bottom, I feel like there should be a way of having a laser pointer where you pointed at this screen and it pointed at all the screens simultaneously. How hard could that be? Yeah, right. And so if you pulled this green one down, there's nothing inhibiting it from moving all the way down there. And so in mathematical braids, those then count as the same braid once you've pulled it down there, because there's nothing holding it in place. So we can't really distinguish between the two. And that's kind of the mathematical explanation. Now, of course, intuitively, you know that you need more than one band to hold that in place just by staring at it. But the mathematical explanation is to do with the equivalence of that braid with the one where the green one is down there. The red and the blue ones are tangled up, and the black one you could move all the way up there. So sometimes mathematics can seem really pointless because it explains things to you that you already know. And that is something that I like to just acknowledge. Because if you pretend that's not true, then people sit there going, oh, well, I already knew that, that's really stupid. And then they give up. So I point out that you start by explaining things you already know to get your brain warmed up. And then you move on to looking at things you didn't already know using the same kind of techniques. Just like if you get a new bicycle, you don't immediately take it up a mountain. You probably try it in front of your house first, and then take it up a mountain once you've understood it a bit. So instead of braiding my hair like that, I made a pie. It's my Bach pie. It's made of banana and chocolate. So I can put my hair up with a pencil because of something to do with mathematics as well. Winding numbers. Torque, not talk. So on to the next thing, factors of 30, which is something that is more obviously mathematical. So I say to everyone, okay, well, can we remember what all the factors of 30 are? There's 1, and then there's 2. Very good. And then there's 3. I know you're a very technical audience. 5, 6, 10, 15, and 30. Very good. And that's pretty boring. A bunch of numbers written in a row. It's not very interesting. So what we can do instead is we can look at the relationships between those numbers. I'm a category theorist, so I'm all about relationships between things. And so I'm going to put 30 at the top, and I'm going to show when anything is a factor of anything else as well. So 6, 10, and 15 are factors of 30 with nothing in between, so they're going to go straight into 30. And 5 goes into 10 and 15, and 2 goes into 6 and 10, and 3 goes into 6 and 15, and then 1 goes into all the ones at the bottom, and then you see that it's the vertices of cube. And this is some kind of... this is some kind of lattice category, but we don't have to say that. And so to me, this is much more interesting than a bunch of numbers in a straight line. And it shows some internal structure. And it shows that if you consider the relationships between things, then you can show some structure that's going on that you didn't otherwise realize was there. And it's amazing. Thank you for the little round of applause. It's amazing sometimes listening to the gasps of astonishment from people who thought that they hated everything about numbers and mathematics. The fact that that turns into a cube. One of the art students, one time she just went, mind blown. So this cube, you can then do something which category theorists know as Poincare duality to it, where you turn the faces of the cube into crossings of a braid. So every two-dimensional face becomes a braid crossing. And you can explain this to people who aren't category theorists or who know anything about Poincare duality by saying, I'm going to wrap this up with ribbon. And because mathematics actually is a world where you can make up any rules you want as long as you stick to them, people like that. I say to them, well, your rules might contain a contradiction, in which case your world implodes, but that's okay. So I never tell my students they're wrong anymore. I just tell them their world imploded. So I have this crossing, and I've decided that every time the ribbon comes across from the right, it's going to be on top. So I need a third color to go down there. And if I try the other half of the cube, then oops, back, then I get this. And that is the third Reidemeister move from knot theory. So as you may know, mathematicians like giving things complicated names because it makes them feel clever. And this is all about feeling clever about yourself. And the cube, the one with the two-dimensional faces, is something from higher dimensional category theory, which is the Yang-Baxter equation. The Yang-Baxter equation appears all over the place. But then as braids, it's the third Reidemeister move, which is what we use to study tangles. And we say, how can we tell if one tangle is the same as another tangle? We have to break down all possible moves, all the possible ways we could pull one string across another. And there are 3 possible moves that generate all the possible things you can do. And that's the third one, which is where you pull one strand across a crossing of another strand. So the first one is where you have a little loop and you just pull it taut. And the second one is where you have 2 things overlapping each other like that, and you pull them apart like that. So this is something that's pretty advanced in higher dimensional category theory. And so in the timeline of me, I wrote that Bach braid when I was an undergraduate, and I found out about this kind of duality when I was a PhD student, and because I was not being very fast at putting 2 and 2 together. It's 4 million, right? It took me about another 10 years after that before I went, hey, what if I do that to the Bach braid? So you can go backwards. You can start with a bunch of 2-dimensional squares and turn it into a braid, or you could start with a braid and put a 2-dimensional square every time there was a crossing. So I tried it on this Bach braid, and I did it in my head first because I'm too lazy to cut up squares of paper. And I did it in my head, and I thought, wait, I think that makes a cube. And I didn't believe it, so then I tore up the worst possible squares you've ever seen, and I stuck them together, and it makes a cube. And so the Bach braid is, in fact, also a cube if you apply Poincare duality to it. And I said this to a friend of mine. I posted it on Facebook, obviously. I was like, oh my God, it's a cube. And my friend said, oh, well, this shows that Bach had a deep knowledge of the Platonic solids inside. I was like, I don't know that that's true. And I don't know that this is helpful. And I don't know that it's useful. And I don't know that it has any point whatsoever, except it's really cool. And sometimes math is just really cool. And the fact that it might have an application at some point, it might happen later. It's like I discovered the other day that the icosahedron, I mean, Euclid came up with the icosahedron 2,000 years ago or something, and they didn't discover any icosahedra anywhere until the middle of the last century, when they discovered that viruses mostly are icosahedral. That's a really long time between thinking of an idea and finding any of them. And I don't know about here, but in the UK, the government demands that our research has impact within 7 years. Anyway, cake is delicious. Cake has impact all the time. This is a Battenberg cake, which is one of my favorite cakes. It's a very English cake. It's something to do with the crest of the Battenberg family. But the main point is that you have 2 colors of cake, and you definitely wouldn't want them next to each other if they were the same color, because that would be terrible. And so you have to have it in this pattern. But this is, of course, it's a very mathematical pattern. And it appears, for example, if you do a multiplication table of 1 and -1. Because in the top left-hand corner, 1 times 1 is 1, usually. 1 times -1 is -1. And -1 times -1 is 1. So it's a Battenberg cake. And you can do this again if you add even and odd numbers, because an even number plus an even number is even, and an odd number plus an even number is, oops, I pressed the button. It's odd. And an odd number plus an odd number is even, so it's a Battenberg cake. And I think that this thing is more sensitive than my thumb. So you can do this with real and imaginary numbers. A real number times a real number is real. And at this point, even if you can't remember what an imaginary number is, you can guess what a real number times an imaginary number probably is, because it's not a trick question. In my class I do this as a trick question. I get them to multiply even and odd numbers as well, and so they all merrily declare that an odd number times an odd number must be an even number. So a real number times an imaginary number is an imaginary number. There's a slight thing about 0, but we'll ignore that. And an imaginary number times an imaginary number is, even if you can't remember what it is, it's probably, given this slide, going to be a real number, and it's a Battenberg cake. So Battenberg cake, this is in fact the cyclic group of order 2, which usually you don't really study until you're in some kind of second year algebra class or something. It's the only possible group of order 2 because there is no other way of arranging the colors of your Battenberg cake. If you try arranging them a different way, you'll just get the same cake, but the other way up. So it's the same thing. And this is related to bed flipping, which is why I've given you all a piece of paper with A, B, C, and D on it, because that's a bed. It looks like a bed, right? We all write A, B, C, and D on our beds in order to remember which way up the bed is. And so mattress, we're supposed to flip our mattress every season to stop our fat bottom from digging in too much to one part of the mattress. I'm much too lazy to do that. The only reason I think about mattress flipping is because of the mathematics behind it. And the idea is that if you start with your head in the A position and you flip it over, you get the D position. If you flip it again, you get the A position, and then you get D, and you get A, and you D. And you'll never achieve B or C, so you have to do something else to get B or C. So you could rotate it to get B, and you could rotate it again to get A, but then you would never get C or D. And so the root of the mathematics of this problem is that it's some kind of group and it's not cyclic because you can't generate it with only one move. So what you can do is you can make a big multiplication table of all the possible moves to see what combinations of moves you could do in order to get every position. So here's the multiplication table. 0 is your me and you never do anything, and so you always stay in the A position. So if we do 0 followed by rotation, then we get in the B position. And if we do 0 followed by flip, so I'm calling flip the sideways flip one, you get into the C position. And if you do 0 followed by flop, flop is the one I'm calling this one because it kind of goes flop if you did it. These are very technical words. D, you get into the D position. And then going down the left-hand column is the same except that you do nothing afterwards. So that's exactly the same. So then slightly more excitingly, we can go down the diagonal. If you do a rotation and then a rotation, you get back into the A position. And if you do a flip and then another flip, you get back into the A position. And if you do a flop and then another flop, you still get back into the A position. And that's the part that tells you that you're doomed to have to do something different, because if you have A's all the way down the diagonal, that tells you whatever you do, if you do it twice, the technical way of saying this is that every element has order 2, which means you get back to the beginning if you do it twice. So now we can try something a little bit more exciting and try doing a rotation followed by a flip, for example. So if we do a rotation and then we do a flip, then you get into the D position. And so this is the part where I've done this with all sorts of people. I've done it with teachers in schools, and it's kind of interesting to see how terrified they get about whether they've done it right or not. And it's that terror that is at the heart of so many people's experience of mathematics, and I want it not to be like that. And once they've discovered that they can flip the piece of paper around and get to the same thing as me, they get really excited because it's like the first thing they ever got right in math for the last 40 years or something. Which is really a shame, but I'm glad to give that to people as a starting point. So now we can try a rotation followed by a flop. So we do a rotation, and then we do a flop. The funniest thing is when you have 6-year-old children doing it faster than their parents and then telling their parents, oh, you're so slow. So then we get to the C position. If we do a flip followed by a rotation, so we start in the A position, we do a flip followed by, what did I say? A rotation. So that should be a D. And then we can do a flip followed by a flop, which should be a B, and then maybe we can start seeing a pattern. So then in the flop followed by the rotation, what do we think should go there?
C.
probably a C. And then what do we think should go in the flop followed by the flip? Probably a B. And then we should probably check that it really was that. So this is something I tell people about math that is surprising to them, that often we proceed in math by guessing, and we justify ourselves after the event. The research would not get anywhere if all we did was take logical steps the whole time. You have to just kind of guess wildly, fly off into the distance, decide whether it was plausible or not, and then gradually fill in the steps slowly. Although it can be really frustrating collaborating with people whose first leap goes a different distance, because you're frantically, I leap really far when I'm first going somewhere, and then I justify myself after the event. And I'm very good at doing that in normal life as well, so I'll come up with an opinion really fast, and then justify it in an extremely watertight way afterwards that sounds like I had a whole logical justification prepared, but I just made it up quickly, which makes me a really annoying person to have an argument with. So we can check that a flop followed by a rotation really was that flop rotation. But the thing about making a leap first and justifying it afterwards can be one of the things that baffles people about trying to do math, because you don't know how you start. You just have to sort of guess. And you have to build up your intuition about how you're going to guess. And intuition in math is just like intuition in life. It's really from past experience. You've kind of built up some experience of things, so you feel your way through. And having a category theoretical intuition can be what really baffles people. Because if you go to a category theory talk, for example, no one ever says what any rules are for anything. They always define something by saying, it's these things subject to the obvious axioms. And all the category theorists in the room go, yeah, well, that's really obvious. And then everyone else goes, what obvious axioms? What? So it's like the things that obviously have to be true. So you get a feel for the things that really ought to be true. Anyway, you could tell that ought to be true, either because you've seen it before, or because you get the feeling that there should be some pattern going on here, or because you feel like there should probably not be two of the same letter next to each other. Yeah?
So you've just proven that the rotation group is actually commutative, right?
The whole group is commutative, in fact, yes. And this gets further. So the first time I did this, I discovered new things about groups that no one had ever told me before, because people are really annoying. They don't tell you things. So the question is, how many Battenberg cakes are in this picture? There's at least 4. So there's these yellow ones. That's not very, well, it depends how close you are. There are these AB ones, which are like yellow ones. And then there's the CD ones, which I'll put as pink. So there's the AD one in the middle, but then the whole thing is 1. Because the whole thing is a Battenberg cake, each of whose cakes was already a Battenberg cake. So it's the iterated Battenberg cake. And this, if you know any group theory, this is the group for the product of the cyclic group of order 2 with itself. And that's when I realized that this is the Cayley table for the group. And this is when I realized that to make the Cayley table for a product, you take the Cayley table for one individual one, but you make it out of little cakes, each of whose cake was the Cayley table for the other one. And no one ever told me that before about products of groups. So this is the iterated Battenberg cake. This is the iterated Battenberg cake. The great thing about making iterated Battenberg cakes is you need to cut so many pieces of cake, you end up with a lot of leftover cake. It's good for making friends. So here I've put the letters on it so you can see how it corresponds. And I like to call this the process of Battenbergification, because what you do is you Battenbergify something. And this is an abstraction. Here's the abstract version of it, where the only information you need, and one of the things about abstraction is that it's efficient. So you think about how efficiently you can express a piece of information. So here, once I've told you we're doing Battenbergification, all I need to tell you for you to get the result is to tell you to what we are applying the Battenbergification. So I need 2 things. So it could be yellow and pink. It could be chocolate and more chocolate, which is good. It could be a bunny and another bunny. Or it could be one kind of Battenberg cake and another kind of Battenberg cake. And that is a slightly better Battenberg cake, iterated Battenberg cake that I made. So an even more efficient way of expressing this information, because I didn't even need to tell you the grid. Once I've told you we're doing Battenbergification, the grid is a given. So all I have to tell you is that the 1 and the 2, what the 1 and the 2 were, and that they're stuck together. So this is a little part of a tree, and the node at the bottom is hiding the information saying, okay, what we're going to do here is Battenbergification to those two things. And so 1 and 2 could be yellow and pink. They could be light brown and dark brown. They could be bunny 1 and bunny 2, or they could be cake 1 and cake 2. But what is cake 1? Cake 1 is one of those, and cake 2 is one of those. So why don't I put the diagram for cake 1 in the place where it says cake 1, and then I can put the diagram for cake 2 in the place where it says cake 2, and then I get a tree. And this is how we start building up mathematical trees, and then we can all get into a fight about whether trees should go up, down, or sideways. But my trees go that way, so if you want it to be upside down, you can just stand on your head, frankly. And I mean, trees just do go that way. That's my... And trees, but the great thing about trees is that we can read them up or down if we feel like it, because we're not real trees, so we don't have to physically grow them. So this tree actually should be read from the top down, because we're talking about taking some ingredients and putting them together. But the great thing about trees is that they can also represent starting from something and splitting them apart. And so taking separate things and putting them together is kind of algebra, and taking some things and splitting them apart is kind of co-algebra. And so if we stick things together, we can stick things, and we can choose how we stick things together. If we don't want to do Battenbergification, we could do something else. And one of the basic trees for sticking 3 things together is like this. So you can put the 2 things on the left together first, and then you can put the thing on the right together with it afterwards. Or you could do it the other way around, where you put the 2 right-hand things together first, and then the thing on the left afterwards. And the basic way that you can then ask if they're equal. So one of the basic things you could do is you could just add numbers together. So we could try adding 4 and 4. 4 add 4 is usually 8. Can be anything you want. You can make it 7, but then your world will implode. You'll be in the 0 group. That's okay, I like the 0 group. The 0 group is where I lived when I was little. It was the number of sweets, candy I ever had, because I was allergic to all of them. So that was my world. It was tragic. If you add 2 afterwards, you get 10. And that's usually written like that because we're such boring people that we write things in straight lines. And this is the whole root of all problems, I think, that we live in a 3-dimensional world, so we write on 2-dimensional pieces of paper, therefore we have to write in 1-dimensional straight lines, which means that we lose all the natural geometry of everything, which is just like when I tidy up the paper on my desk. It starts with natural 2-dimensional geometry. If I put them in a pile, I've forced it into 1 dimension, and so I've lost all its natural geometry. That's my theory, and I'm sticking to it. If I do it the other way around, then I add 4 and 2 first, which is usually 6. And then if I add the 4 afterwards, mostly it's 10. And we write it that way around with the parentheses. And so these two are considered to be equal when you're adding numbers together, which is the associative law. They're not really equal because, as we know, all equations are lies unless they're completely useless. Because the only equation that's really honestly true is the one that says x equals x, where x is something. Because all the other ones aren't really equal. That thing on the left isn't really equal to the thing on the right. It's only the end result that's equal. The thing on the left is manifestly different. It's visibly, evidently different from the thing on the right. And the equation, if the 2 things on either side of the equation were actually the same, then the equation would be pointless because we would just have something that was the same as something else. We wouldn't have achieved anything. So one of the things that gets people who hate math really excited is when I tell them that all equations are lies, because they have felt like the equations were all kind of things being equal to other things is pointless. So what you have to do is see what was different about the left and the right that actually achieved you anything at all. And here, for a small child, it's possible that the thing on the left is easier than the thing on the right, because 4 add 4 might be something easier than 4 add 2, because you kind of learn how to add the same number to each other. And it's the same with the commutativity. The fact that 20 plus 2 equals 2 plus 20 is really important when you're little, because if you try and do 2 plus 20, you put 2 in your head and then you count on 20, and that's a disaster. And so the fact that those things are equal, it's only the end result that's equal. It's not the process that's equal. And when you're doing category theory, you're really interested in the process and not just the end result. And in fact, when you're doing math, real math, not school math, is more about the process of getting somewhere than just the end result. And so this associativity thing hides a lot of information that category theorists like to bring out again, because the more interesting your objects become, the more interesting the difference becomes between those two processes. For example, if you do this with egg yolks and sugar, and you put egg yolks and sugar together, and then you add milk with some heat, you get custard. Whereas if you mix sugar and milk together first, and then you add egg yolks afterwards, you do not get custard. So these two things are not equal. You might ask if they're isomorphic. Now, if you do it with cake, it doesn't really matter. So most cake, old-fashioned cake recipes say cream the butter and sugar and the butter, then beat in the eggs, and then fold in the flour at the end. But in fact, especially if you have an electric whisk, you can just kind of chuck everything in and go, and it's basically the same thing. So up to a certain amount of something, I would say those are kind of isomorphic. And in fact, I tried it with my students for a laugh, doing all the possible different combinations. So here are all the different combinations. This is the McLean pentagon for associativity, but basically it's all the different ways of making cake. And we're not doing commutativity of cake ingredients, we're just doing associativity. So for example, this top left tree is the one where, first of all, you mix the butter and the eggs. That's really disgusting. It kind of looks like vomit for a while. And then you put the sugar in and it stays looking really disgusting. But actually, once you've put the flour in, if you beat hard enough, it all kind of turns out all right. And it's the same with all those other ones. The one at the bottom is kind of interesting, because the one at the bottom is the one where you need two bowls. Because you have to mix the butter and the sugar first, and then you also have to mix the eggs and the flour, which is kind of gross. And then you put them all together in one bowl. And so the thing is that the end result is the same, but the amount of effort you have to make in the middle is very, very different. Because if you don't do it in the standard order, then it looks, first of all, it looks really gross in the middle. And secondly, it takes a lot more effort then to get it to look all right in the end. And so you might or might not care about it looking gross in the middle. And if you have an electric whisk, you might not care about the amount of effort. But if you're doing it with a wooden spoon, then it's really quite a lot of effort. So these things are all about the context in which you are, which is kind of secretly saying, what category are you in? Are you in the category that contains whisks or not? And so this is... this pentagon depicts the relationships between those trees, where the top little arrow shows that you can move the middle branch across a node, and each of the arrows in the pentagon shows moving one branch across a node. So if we start at the left-hand tree, then to get to the next one up, on top, we move the second branch across the thing, and then we move the branch that's got a little sub-branch, and we take the whole thing and its sub-branch with it, and then we move the little one back off again, which is kind of less efficient than the bottom route, where we move the one branch and then we move the other branch. But that is the associativity pentagon, which you don't usually see until you take a category theory course, which you might not do, well, ever, but you might not do until you're a grad student or something. And yet, I explain this to 7-year-old children. So why do we make everyone do stuff like quadratic equations and the double angle rule for sine and cosine, which is really boring, instead of showing these things, which are kind of cool and different? And then you can say, well, what if I wanted to make chocolate cake? So then I need another ingredient, and then I need another leaf on my tree, and then I need to draw more pentagons like that, showing how the 5-leaf trees all interact with each other. And if you're me, you're sitting in a cafe one day when you're a grad student going, I wonder what this looks like. And so you sit and kind of cut things out and make things together. And it makes a pretty cool shape, which there's a picture of it in my book. There's a net of it on my webpage, so you can cut it out and build it make it as a thing. And none of the books I read before then actually showed that geometrical structure. So the pentagon is shown as a pentagon. The next one up is just a kind of... Whereas the whole point of drawing these relationships between things is to bring out some structure so that we can use a different type of intuition. Because if we only have access to our mathematical intuition, it's hard to build it up because you can't get access to any more of it because you've only got it. Whereas if you can bring in intuition from other places, then it means that you have something to build on. So if you can bring in your geometrical intuition as well, then it's a way that you can make advances more quickly. And so I made a nice symmetrical version of the next one of these up. And someone wrote to me, someone always writes to me saying something like, oh, you're really stupid. It's always that. So someone wrote to me and said, oh, well, this doesn't work because you couldn't make this out of something rigid like metal because the angles don't match up, something, something, something. Because you have some pentagons and some squares, and sometimes two pentagons meet. On one side there's a pentagon, on one side there's a square. So the angle of incidence is different on both sides, which means it's got a little twisted. And so he said, well, so you couldn't make this out of metal. And I was like, I never said I was going to make it out of metal. So there's always that. But then when I get people to build these things together, then you use a combination of your geometrical intuition and your knowledge about the trees. Just like when we did the iterated Battenberg cake, we kind of spotted patterns and we faffed around with a thing. And it's often a combination of those things that makes mathematics go. It's a combination of spotting patterns, actually doing calculations, or as I call it, thinking with your brain. And that if you're allowed to do both of those things and put them together, then you get a lot further. And so that is my explanation. It's how I like to show people what abstraction and abstract mathematics, the range of things that it can do. And then finally, I put it to you that if mathematics is the logical study of logical things, and category theory is the mathematics of mathematics. It's how mathematics works. And just like if you don't care about how logical things work, you kind of won't care about mathematics. So if you don't really care about how mathematics works, then you don't care about category theory either. But if you want to, if you're intrigued, if you're me, then you keep asking why. You don't just want to know if something is true. You want to know why it's true. And then every time you ask yourself why it's true more, you get further and further into having to explain how things work. And for me, category theory explains how mathematics works, how the structures of mathematics work, how the logic inside mathematics works. And that means that if you do a bit of substitution in these sentences, then it's the logical study of the logical study of how logical things work. And I have found it much easier to explain category theory like this to everybody who isn't a mathematician than the hardest audience. I think there are two really hard audiences. Engineers who just... Are there any engineers in the room? I mean, actual engineers. who are so convinced, and certainly the engineering department at the University of Sheffield, they're convinced that mathematics simply exists to make engineering work. And that there's no point doing any mathematics that doesn't make engineering work. So they're a very difficult audience. But the really difficult audience is pure mathematicians who don't want to have to think about category theory. And so they're especially non-commutative algebraists, I reckon, they're so determined that they're kind of affronted by the idea that there's something that could possibly have any role in explaining what they do, that they don't want to know. But everyone else thinks it's great, and I hope that you'll feel like it's possible to explain abstract things to people as well. Thank you very much.
So we have time for discussion. There are floor mics, so if people would like to come up to the floor mics, I guess if you want to take questions or if anyone has anything to say. Come up to the floor mic.
Hey.
Hi.
I really enjoyed your book. And
Oh, thanks.
I was really curious about kind of like what do you recommend is the next step for getting into category theory? What resources? Obviously, Catsters, but what do you recommend?
Are you ready to get technical?
Sure, why not? Hit me with that.
Well, there's Tom Leinster's book, which
Tom Leinster's? Mm-hmm. Okay.
Which is it's not as difficult as McLean's book.
Okay.
There's also Steve Audie's book. I think that Steve Audie's book is more difficult than Tom Leinster's book. I think Leinster's book has more examples and is a little more chatty.
Okay. So Steve Lunster and
Tom Leinster. Yeah, you did a commutativity.
Steve Albee.
Yeah.
Okay, I'll look that up. Thank you.
So you've discovered these useful explanatory cases, such as braids and factors of 30 and bed flipping and so forth. I'd like to know, though, about some failed experiments, some explanatory
Nothing I do
ideas
fails.
that you. Well, that's okay. But supposing that isn't the case,
something I tried to explain that failed.
like an explanatory methodology that failed, or so.
I think I've blocked it all out of my consciousness. I'm not trying to be ridiculous. I just am ridiculous. I don't have to try. Let me think. Something that failed. Well, this didn't exactly fail. I rescued it. But there was a thing, if you read my book, there's a bit where I talk about frozen eggs. So I'm trying to explain invertibility and pseudo-invertibility, where you can invert a process and you get something that's more or less the same as what you started with, depending on what you care about. So I once froze some eggs and discovered that if you freeze eggs and then thaw them again, and if you crack them afterwards, then it's really bizarre because the white is completely normal, but the yolk is really strange. It looks like it's been boiled, except it hasn't. And so if you crack the egg in a bowl, then the white looks like a normal white, and then the yolk stands up in a kind of really solid sphere. So it looks extremely strange. And then if you poke it open, then it looks like it's been boiled. Now, as it happens, I eat a lot of egg whites without the yolk. So not only is this, do I not care about the yolk, it's actually easier to separate because you can just pick the yolk up and chuck it out. And so I decided to do this with my students. I thought, well, what I'll do is I'll freeze some eggs and thaw them, and then I'll ask them to tell them apart by cracking them and looking and seeing what's different. And so I put them in the freezer, and they just all cracked. Because I'd forgotten this aspect of it, because when I was doing it before, I didn't care about whether I could tell which ones were pre-frozen or not. So I forgot that obviously if you freeze some liquid, it expands, and so the shells all cracked. So that was a kind of failure, except that when I took them into class, none of the students noticed that I was handing them eggs that had cracks in them. So it kind of unfailed itself. I don't know, does that count as a...
Well, as long as it wasn't the whole class got perfect scores mysteriously.
No, it wasn't that. I mean, the thing about the cake is that when I'm actually teaching algebra classes, I do the cake thing because I'm trying to get students to remember that there are two different possible groups of order 4, and one of them is cyclic and one of them isn't. And so I try and explain it as one of them being the iterated Battenberg cake and the other one not. And some of them get it, so in their final exam they'll go, "It's the iterated Battenberg cake!" But then some of them, of course, still don't. I mean, no matter what you do, it's when you mark the exams you get depressed and you feel like you failed because there's always someone who doesn't, there's more people who don't do it right than you ever wanted. But so that's kind of a failure, I guess. Yay, failure. The way I like to think about failure, and I say this to people, is that unless you fail, you don't know where your boundaries are. Because failure is finding where your boundaries are. And if you're interested in finding your boundaries, you have to fail to find them, because that is where your boundary is. Some people aren't interested in finding their boundaries. I'm interested in finding my boundaries, so failing is okay. Thanks.
This is going to sound like another failure question, but it isn't really meant that way. So you said you're good at sort of making intuitive leaps and then filling things in, afterwards. And of course, in like a normal argument, you can just kind of make up justifications. But in math, you have to actually have been right in the way you leaped. And have you run into cases where you've made a leap and beaten your head against it for a long time, and you couldn't actually get there?
Yeah, definitely, loads of times. And I like to think that I just haven't got there yet, because my reason for making that leap, when you do category theory, the reason that you have for making the leap is so strong, it just doesn't count as a proof yet. And so there's that thing about morality when you say that morally this is... And in some branches of math, when you say morally this is true, what they mean is it's not really true. It's just almost true. But in category theory, you often mean that there's some profound categorical kind of explanation for why it's true. You just haven't turned it into a proof yet. And often the reason that you haven't turned it into a proof yet is that there's some higher dimensional argument that ought to be true, but you haven't got the technical details right. At least in what I do, it's often because what you need is coherence for tetracategories or something. And that you know that coherence for tetracategories has to work. It's just that no one's done it yet because we haven't figured out ways of squashing it onto two-dimensional pages yet. And so people are trying to work with making time another dimension so that you have movie slices through arguments, but it's just very difficult to work with. And now there are computer implementations of higher dimensional category theory proofs, but I can't get my head around them yet. Partly because they're all done in Poincaré duals, and my brain doesn't think like that. So perhaps they're just all going to go off and do Poincaré dual coherence without me. It's all right. I've got cake.
I'm a big fan, love the book.
Thanks.
I don't cook. So I was wondering if there's the moral equivalent for music.
Oh, well, that's a really interesting question because I'm being asked to write it. That might be the next thing I write.
Because I noticed when you did the clock example, you dismissed it as being, well, that's all really kind of silly.
Wait, did I? What?
In the book, you when you were talking about using the clock and adding, and when you in a sense add 7 and 7 in a clock, you end up with.
I don't feel like I said it was silly, but did I?
Maybe I mistook. I don't know. But I was thinking that if you take intervals and not in the major minor, I mean not in the major minor sense, but in a sequence of 0 to 12 or 0 to 11, then in a sense suddenly that's very useful when you want to add intervals to get to other tones.
Yeah, to see what the next note up is. Yeah, and things like the cycle of fifths as it goes round the 12 notes, and how many times you have to go around the cycle of fifths before you get to the same note. That kind of stuff. Yes.
So I'm looking forward to the book.
Thank you. Hi.
Thanks for the great talk. So it's always frustrating when the lay public thinks mathematics is just about numbers.
Yeah.
But it's even more frustrating when professional technical people such as engineers and mathematicians, a subset of mathematicians, also think that. So I'm just wondering if you have some advice on how to communicate the fact that much of mathematics, like category theory, is about some other kind of structures.
I think that one has to acknowledge that mathematics does kind of start with stuff about numbers, but that the techniques that you use to study numbers, it turns out you can use to study more things than numbers, such as shapes. And people are often okay with the idea of mathematics being about shapes because they've done geometry. When you start saying that mathematics can be about patterns in other things, then you can get into shaky ground. But the thing I find really funny is when non-mathematicians accuse me of calling something math that they reckon isn't math, as if somehow they're better qualified to say what is and isn't math than I am. But it does even happen. I mean, it's the ultimate insult in category theory conferences. Someone will stand up and go, well, that's all very well, but that's not mathematics. And I always want to say, and it's always some grumpy old person, but, sorry, people. I said grumpy. Right. Anyway, and I always want to stand up and say, well, what do you think mathematics is? And so then if they say that they think so a category theorist would never say mathematics is just the study of numbers. But if you say that mathematics is the study of numbers and that you use that as a justification of mathematics being the study of numbers, that's kind of evidence right there you're not a very good mathematician, because that's just P implies P. But when category theorists say that, I don't know what they mean. I think they mean that usually it means that they're upset that mathematics is going in a direction that isn't their direction. And usually what they mean is that when they were young, everyone told them they were going to be the world's greatest mathematician, and then it turned out not to be the case, and that they haven't recovered from that yet. That's what they usually mean. And so I think it's important to decide when the people are the lost causes and they're not going to get it, and why it is they're so determined. So sometimes it's the people who are already good at something and they don't want to admit that anyone else might be good at mathematics because they get so much of their own self-esteem from being good at something they reckon other people can't do. And if it's that, then their reason for thinking that this stuff isn't math is not generous, and it also doesn't matter. Whereas the people who I think matter more when it comes to persuading them that math isn't just about numbers, well, there's stuff like the government who make math curriculums. That's a whole different thing. I'm not quite sure how to persuade them yet. But you can use examples of where math has helped in normal life, but I don't like doing that because I feel like that's kind of disingenuous. Because I really don't think that the importance of math comes from the way that the fact that it is kind of somehow at the root of curing illness. I think that's cheating as a way of explaining why math is useful. And there's the old thing about, oh yeah, number theory, cryptography, the internet, blah blah blah. But that's kind of numbers again. So on the whole, it's difficult, and I think acknowledging that there is some truth to what people are saying is always a good start in persuading them to expand their thinking a little bit.